It has long been known that mechanical work can be converted into heat and that a given amount of heat contains the energy equivalent of a certain amount of mechanical work. Heat and work are theoretically interchangeable and bear a fixed relation to each other. Heat can therefore be measured in work units, for example, FTLB, as well as in heat units. The British thermal unit, BTU, of heat is the quantity of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. It is equivalent to 778 FTLB of mechanical work. A pound of petroleum fuel, when burned with enough air to consume it completely, gives up about 20,000 BTU, the equivalent of 15,560,000 FTLB of mechanical work. These quantities express the heat energy of the fuel in heat and work units, respectively. The ratio of useful work done by an engine to the heat energy of the fuel it uses, expressed in work or heat units, is called the thermal efficiency of the engine. If two similar engines use equal amounts of fuel, the engine that converts into work the greater part of the energy in the fuel, higher thermal efficiency, delivers the greater amount of power. Furthermore, the engine that has the higher thermal efficiency has less waste heat to dispose of to the valves, cylinders, pistons, and cooling system of the engine. A high thermal efficiency also means low specific fuel consumption and, therefore, less fuel for a flight of a given distance at a given power. Thus, the practical importance of a high thermal efficiency is threefold, and it constitutes one of the most desirable features in the performance of an aircraft engine. Of the total heat produced, 25 to 30% is utilized for power output, 15 to 20% is lost in cooling, heat radiated from cylinder head fins, 5 to 10% is lost in overcoming friction of moving parts, and 40 to 45% is lost through the exhaust. Anything that increases the heat content going into mechanical work on the piston, which reduces the friction and pumping losses, or which reduces the quantity of unburned fuel or the heat lost to the engine parts, increases the thermal efficiency. The portion of the total heat of combustion that is turned into mechanical work depends to a great extent upon the compression ratio. The compression ratio is the ratio of the piston displacement plus combustion chamber space to the combustion chamber space, as mentioned earlier. Other things being equal, the higher the compression ratio is, the larger is the proportion of the heat energy of combustion turned into useful work at the crankshaft. On the other hand, increasing the compression ratio increases the cylinder head temperature. This is a limiting factor because the extremely high temperature created by high compression ratios causes the material in the cylinder to deteriorate rapidly and the fuel to detonate instead of burning at a controlled rate. The thermal efficiency of an engine may be based on either bhp or indicated horsepower, IP, and is represented by the following formula. Indicated thermal efficiency equals IP times 33,000. Weight of fuel burned / min times heat value times 778. The formula for brake thermal efficiency is the same as shown above, except the value for bhp is inserted instead of the value for IP. Example. An engine delivers 85 brake horsepower for a period of 1 hour and during that time consumes 50 pounds of fuel. Assuming the fuel has a heat content of 18,800 BTU per pound, find the thermal efficiency of the engine. 8.5 IP x 33,000 divided by 0.833 x 18,800 BTU x 778 is equal to 2,805,000 divided by 12,184,569. Brake thermal efficiency equals 0.23 or 23%. End of page 1 to 34. Reciprocating engines are only about 34% thermally efficient, that is, they transform only about 34% of the total heat potential of the burning fuel into mechanical energy. The remainder of the heat is lost through the exhaust gases, the cooling system, and the friction within the engine. Thermal distribution in a reciprocating engine is illustrated in Figure 1.42. Mechanical efficiency. Mechanical efficiency is the ratio that shows how much of the power developed by the expanding gases in the cylinder is actually delivered to the output shaft. It is a comparison between the bhp and the IP. It can be expressed by the following formula. Mechanical efficiency equals bhp divided by ihp. Brake horsepower is the useful power delivered to the propeller shaft. Indicated horsepower is the total HP developed in the cylinders. The difference between the two is friction horsepower, FHP, the power lost in overcoming friction. The factor that has the greatest effect on mechanical efficiency is the friction within the engine itself. The friction between moving parts in an engine remains practically constant throughout an engine's speed range. Therefore, the mechanical efficiency of an engine is highest when the engine is running at the RPM at which maximum bhp is developed. Mechanical efficiency of the average aircraft reciprocating engine approaches 90%. Volumetric efficiency. Volumetric efficiency is a ratio expressed in terms of percentages. It is a comparison of the volume of air-fuel charge, corrected for temperature and pressure, inducted into the cylinders to the total piston displacement of the engine. Various factors cause departure from a 100% volumetric efficiency. The pistons of a naturally aspirated engine displace the same volume each time they travel from top center to bottom center of the cylinders. The amount of charge that fills this volume on the intake stroke depends on the existing pressure and temperature of the surrounding atmosphere. Therefore, to find the volumetric efficiency of an engine, standards for atmospheric pressure and temperature had to be established. The U.S. standard atmosphere was established in 1958 and provides the necessary pressure and temperature values to calculate volumetric efficiency. The standard sea level temperature is 59 degrees Fahrenheit, or 15 degrees Celsius. At this temperature, the pressure of 1 atmosphere is 14.69 lb/in2, and this pressure supports a column of mercury Hg 29.92 inches high, or 29.92 Hg. These standard sea level conditions determine a standard density, and if the engine draws in a volume of charge of this density exactly equal to its piston displacement, it is said to be operating at 100% volumetric efficiency. An engine drawing in less volume than this has a volumetric efficiency lower than 100%. An engine equipped with true supercharging, boost above 30.00 Hg, may have a volumetric efficiency greater than 100%. The equation for volumetric efficiency is as follows. Volumetric efficiency equals volume of charge, corrected for temperature and pressure, divided by piston displacement. Many factors decrease volumetric efficiency, including 1. Part throttle operation. 2. Long intake pipes of small diameter. 3. Sharp bends in the induction system. 4. Carburetor air temperature too high. 5. Cylinder head temperature too high. 6. Incomplete scavenging, and 7. Improper valve timing. End of page 1 to 35. Propulsive efficiency. A propeller is used with an engine to provide thrust. The engine supplies bhp through a rotating shaft, and the propeller absorbs the bhp and converts it into thrust hp. In this conversion, some power is wasted. Since the efficiency of any machine is the ratio of useful power output to the power input, propulsive efficiency, in this case, propeller efficiency, is the ratio of thrust hp to bhp. On the average, thrust HP constitutes approximately 80% of the bhp. The other 20% is lost in friction and slippage. Controlling the blade angle of the propeller is the best method of obtaining maximum propulsive efficiency for all conditions encountered in flight. During takeoff, when the aircraft is moving at low speeds and when maximum power and thrust are required, a low propeller blade angle gives maximum thrust. For high-speed flying or diving, the blade angle is increased to obtain maximum thrust and efficiency. The constant speed propeller is used to give required thrust at maximum efficiency for all flight conditions. Gas turbine engines. Types and construction. In a reciprocating engine, the functions of intake, compression, combustion, and exhaust all take place in the same combustion chamber. Consequently, each must have exclusive occupancy of the chamber during its respective part of the combustion cycle. A significant feature of the gas turbine engine is that separate sections are devoted to each function, and all functions are performed simultaneously without interruption. A typical gas turbine engine consists of 1. An air inlet. 2. Compressor section. 3. Combustion section. 4. Turbine section. 5. Exhaust section. 6. Accessory section, and 7. The systems necessary for starting, lubrication, fuel supply, and auxiliary purposes such as anti-icing, cooling, and pressurization. The major components of all gas turbine engines are basically the same. However, the nomenclature of the component parts of various engines currently in use varies slightly due to the difference in each manufacturer's terminology. These differences are reflected in the applicable maintenance manuals. One of the greatest single factors influencing the construction features of any gas turbine engine is the type of compressor or compressors for which the engine is designed. Four types of gas turbine engines are used to propel and power aircraft. They are the turbofan, turboprop, turboshaft, and turbojet. The term turbojet was used to describe any gas turbine engine used in aircraft. As gas turbine technology evolved, these other engine types were developed to take the place of the pure turbojet engine. The turbojet engine has problems with noise and fuel consumption in the speed range that airliners fly, 0.8 Mach. Due to these problems, use of pure turbojet engines is very limited. So, almost all airliner-type aircraft use a turbofan engine. It was developed to turn a large fan or set of fans at the front of the engine and produces about 80% of the thrust from the engine. This engine was quieter and had better fuel consumption in this speed range. Turbofan engines have more than one shaft in the engine, many are two-shaft engines. This means that there are two sets of compressors and turbines that drive them. These two-shafted engines use two spools. A spool is a compressor and a shaft in turbines that drive that compressor. In a two-spool engine, there is a high-pressure spool and a low-pressure spool. The low-pressure spool generally contains the fans and the turbine stages it takes to drive them. The high-pressure spool is the high-pressure compressor, shaft, and turbines. This spool makes up the core of the engine, and this is where the combustion section is located. Turbofan engines can be low bypass or high bypass. The amount of air that is bypassed around the core of the engine determines the bypass ratio. As can be seen in Figure 1.43. The air generally driven by the fan does not pass through the internal working core of the engine. The amount of airflow in lb/SCC from the fan bypass to the core flow of the engine is the bypass ratio. Bypass ratio equals 100 pounds ASCC flow fan divided by 20 pounds a second. Flow core equals 5:1 bypass ratio. Some low bypass turbofan engines are used in speed ranges above 0.8 Mach, military aircraft. These engines use augmenters or afterburners to increase thrust. By adding more fuel nozzles and a flame holder in the exhaust system, extra fuel can be sprayed and burned, which can give large increases in thrust for short amounts of time. The turboprop engine is a gas turbine engine that turns a propeller through a speed reduction gearbox. This type of engine is most efficient in the 300 to 400 miles per hour speed range and can use shorter runways than other aircraft. End of page 1 to 36. Approximately 80 to 85% of the energy developed by the gas turbine engine is used to drive the propeller. The rest of the available energy exits the exhaust as thrust. By adding the horsepower developed by the engine shaft and the horsepower in the exiting thrust, the answer is equivalent shaft horsepower. With regard to aircraft, the turboshaft engine is a gas turbine engine made to transfer horsepower to a shaft that turns a helicopter transmission or is an onboard auxiliary power unit, APU. An APU is used on turbine-powered aircraft to provide electrical power and bleed air on the ground and a backup generator in flight. Turboshaft engines can come in many different styles, shapes, and horsepower ranges. Air entrance. The air entrance is designed to conduct incoming air to the compressor with a minimum energy loss resulting from drag or ram pressure loss. That is, the flow of air into the compressor should be free of turbulence to achieve maximum operating efficiency. Proper inlet design contributes materially to aircraft performance by increasing the ratio of compressor discharge pressure to duct inlet pressure. This is also referred to as the compressor pressure ratio. This ratio is the outlet pressure divided by the inlet pressure. The amount of air passing through the engine is dependent upon three factors. 1. The compressor speed, RPM. 2. The forward speed of the aircraft. 3. The density of the ambient, surrounding, air. Turbine inlet type is dictated by the type of gas turbine engine. A high-bypass turbofan engine inlet is completely different from a turboprop or turboshaft inlet. Large gas turbine-powered aircraft almost always have a turbofan engine. The inlet on this type of engine is bolted to the front, a flange, of the engine. These engines are mounted on the wings, or nacelles, on the aft fuselage, and a few are in the vertical fin. A typical turbofan inlet can be seen in Figure 1.44. Since on most modern turbofan engines the huge fan is the first part of the aircraft the incoming air comes into contact with, icing protection must be provided. This prevents chunks of ice from forming on the leading edge of the inlet, breaking loose, and damaging the fan. Warm air is bled from the engine's compressor and is ducted through the inlet to prevent ice from forming. If inlet guide vanes are used to straighten the airflow, then they also have anti-icing air flowing through them. The inlet also contains some sound-reducing materials that absorb the fan noise and make the engine quieter. Turboprops and turboshafts can use an inlet screen to help filter out ice or debris from entering the engine. A deflector vane and a heated inlet lip are used to prevent ice from forming and allowing large chunks to enter the engine. On military aircraft, the divided entrance permits the use of very short ducts with a resultant small pressure drop through skin friction. Military aircraft can fly at speeds above Mach 1, but the airflow through the engine must always stay below Mach 1. Supersonic airflow in the engine would destroy the engine. By using convergent and divergent shaped ducts, the airflow is controlled and dropped to subsonic speeds before entering the engine. Supersonic inlets are used to slow the incoming engine air to less than Mach 1 before it enters the engine. End of page 1 to 37. Accessory Section. The accessory section of the gas turbine engine has various functions. The primary function is to provide space for the mounting of accessories necessary for operation and control of the engine. Generally, it also includes accessories concerned with the aircraft, such as electric generators and hydraulic pumps. Secondary functions include acting as an oil reservoir and/or oil sump and housing the accessory drive gears and reduction gears. The arrangement and driving of accessories has always been a major problem on gas turbine engines. Driven accessories on turbofans are usually mounted on the accessory gearbox, which is on the bottom of the engine. The location of the accessory gearbox varies somewhat, but most turboprops and turboshafts have the accessory cases mounted to the back section of the engine. The components of the accessory section of all gas turbine engines have essentially the same purpose, even though they often differ quite extensively in construction details and nomenclature. The basic elements of the accessory section are: 1. The accessory case, which has machined mounting pads for the engine-driven accessories, and 2. The gear train, which is housed within the accessory case. The accessory case may be designed to act as an oil reservoir. If an oil tank is utilized, a sump is usually provided below the front bearing support for the drainage and scavenging of oil used to lubricate bearings and drive gears. The accessory case is also provided with adequate tubing or cord passages for spraying lubricating oil on the gear train and supporting bearings. The gear train is driven by the engine high-pressure compressor through an accessory drive shaft, tower shaft, gear coupling, which splines with a gearbox gear and the high-pressure compressor. The reduction gearing within the case provides suitable drive speeds for each engine accessory or component. Because the rotor operating RPM is so high, the accessory reduction gear ratios are relatively high. The accessory drives are supported by ball bearings assembled in the mounting pad bores of the accessory case. Figure 1.45. Compressor Section. The compressor section of the gas turbine engine has many functions. Its primary function is to supply air in sufficient quantity to satisfy the requirements of the combustion burners. Specifically, to fulfill its purpose, the compressor must increase the pressure of the mass of air received from the air inlet duct, and then discharge it to the burners in the quantity and at the pressures required. A secondary function of the compressor is to supply bleed air for various purposes in the engine and aircraft. The bleed air is taken from any of the various pressure stages of the compressor. The exact location of the bleed ports is, of course, dependent on the pressure or temperature required for a particular job. The ports are small openings in the compressor case adjacent to the particular stage from which the air is to be bled, thus, varying degrees of pressure are available simply by tapping into the appropriate stage. Air is often bled from the final or highest pressure stage since, at this point, pressure and air temperature are at a maximum. At times it may be necessary to cool this high-pressure air. If it is used for cabin pressurization or other purposes to which excess heat would be uncomfortable or detrimental, the air is sent through an air conditioning unit before it enters the cabin. Bleed air is utilized in a wide variety of ways. Some of the current applications of bleed air are: 1. Cabin pressurization, heating, and cooling. 2. De-icing and anti-icing equipment. 3. Pneumatic starting of engines, and 4. Auxiliary drive units, ADU. Another function of the compressor bleed air is for the operation of vortex dissipators. The vortex dissipator supplies a high-velocity stream of compressor bleed air blown from a nozzle into an area where vortices are likely to form. Vortex dissipators destroy the vortices that would otherwise suck debris from the ground into engines mounted in pods that are low to the ground. Compressor types. The two principal types of compressors currently being used in gas turbine aircraft engines are centrifugal flow and axial flow. The centrifugal flow compressor achieves its purpose by picking up the entering air and accelerating it outwardly by centrifugal action. The axial flow compressor compresses air while the air continues in its original direction of flow, thus avoiding the energy loss caused by turns. The components of each of these two types of compressor have their individual functions in the compression of air for the combustion section. A stage in a compressor is considered to be a rise in pressure. Centrifugal flow compressors. The centrifugal flow compressor consists of an impeller, rotor, a diffuser, stator, and a compressor manifold. Figure 1:46. Centrifugal compressors have a high pressure rise per stage that can be around 8:1. Generally, centrifugal compressors are limited to 2 stages due to efficiency concerns. End of page 1-38. The two main functional elements are the impeller and the diffuser. Although the diffuser is a separate unit and is placed inside and bolted to the manifold, the entire assembly, diffuser and manifold, is often referred to as the diffuser. For clarification during compressor familiarization, the units are treated individually. The impeller is usually made from forged aluminum alloy, heat-treated, machined, and smoothed for minimum flow restriction and turbulence. In most types, the impeller is fabricated from a single forging. This type impeller is shown in Figure 1:46. The impeller, whose function is to pick up and accelerate the air outwardly to the diffuser, may be either of two types: single entry or double entry. The principal differences between the two types of impellers are size and ducting arrangement. The double entry type has a smaller diameter but is usually operated at a higher rotational speed to assure sufficient airflow. The single entry impeller, shown in Figure 1:47, permits convenient ducting directly to the impeller eye, inducer vanes, as opposed to the more complicated ducting necessary to reach the rear side of the double entry type. Although slightly more efficient in receiving air, the single entry impeller must be large in diameter to deliver the same quantity of air as the double entry type. This, of course, increases the overall diameter of the engine. Included in the ducting for double entry compressor engines is the plenum chamber. This chamber is necessary for a double entry compressor because the air must enter the engine at almost right angles to the engine axis. Therefore, in order to give a positive flow, the air must surround the engine compressor at a positive pressure before entering the compressor. Included in some installations as necessary parts of the plenum chamber are the auxiliary air intake doors, blow-in doors. These blow-in doors admit air to the engine compartment during ground operation, when air requirements for the engine are in excess of the airflow through the inlet ducts. The doors are held closed by spring action when the engine is not operating. During operation, however, the doors open automatically whenever engine compartment pressure drops below atmospheric pressure. During takeoff and flight, ram air pressure in the engine compartment aids the springs in holding the doors closed. The diffuser is an annular chamber provided with a number of vanes forming a series of divergent passages into the manifold. The diffuser vanes direct the flow of air from the impeller to the manifold at an angle designed to retain the maximum amount of energy imparted by the impeller. They also deliver the air to the manifold at a velocity and pressure satisfactory for use in the combustion chambers. Refer to Figure 1:46a. And note the arrow indicating the path of airflow through the diffuser, then through the manifold. The compressor manifold shown in Figure 1, 46A, diverts the flow of air from the diffuser, which is an integral part of the manifold, into the combustion chambers. The manifold has one outlet port for each chamber so that the air is evenly divided. A compressor outlet elbow is bolted to each of the outlet ports. These air outlets are constructed in the form of ducts and are known by a variety of names, such as air outlet ducts, outlet elbows, or combustion chamber inlet ducts. Regardless of the terminology used, these outlet ducts perform a very important part of the diffusion process, that is, they change the radial direction of the airflow to an axial direction, in which the diffusion process is completed after the turn. To help the elbows perform this function in an efficient manner, turning vanes, cascade vanes, are sometimes fitted inside the elbows. These vanes reduce air pressure losses by presenting a smooth, turning surface. Figure 1, 46B. End of page 1 to 39. Axial-Flow Compressor. The axial-flow compressor is a combination of an engine compressor and high-pressure turbine that drives it using a connecting drive shaft. In a single-spool engine, a high-pressure turbine drives the entire compressor. In a dual-spool engine, the compressor and high-pressure turbine are both split into two segments. Each compressor segment is driven by its corresponding turbine using two separate drive shafts, with one inside the other. The first stage turbine drives the N2 compressor. The axial-flow compressor has two main elements, a rotor and a stator. The rotor has blades fixed on a spindle. These blades impel air rearward in the same manner as a propeller because of their angle and airfoil contour. The rotor, turning at high speed, takes in air at the compressor inlet and impels it through a series of stages. From inlet to exit, the air flows along an axial path and is compressed at a ratio of approximately 1.25 to 1 per stage. The action of the rotor increases the compression of the air at each stage and accelerates it rearward through several stages. With this increased velocity, energy is transferred from the compressor to the air in the form of velocity energy. The stator blades act as diffusers at each stage, partially converting high velocity to pressure. Each consecutive pair of rotor and stator blades constitutes a pressure stage. The number of rows of blades, stages, is determined by the amount of air and total pressure rise required. Compressor pressure ratio increases with the number of compression stages. Most engines utilize up to 16 stages and more. The stator has rows of vanes, which are in turn attached inside an enclosing case. The stator vanes, which are stationary, project radially toward the rotor axis and fit closely on either side of each stage of the rotor blades. In some cases, the compressor case, into which the stator vanes are fitted, is horizontally divided into halves. Either the upper or lower half may be removed for inspection or maintenance of rotor and stator blades. The function of the stator vanes is to receive air from the air inlet duct or from each preceding stage and increase the pressure of the air and deliver it to the next stage at the correct velocity and pressure. They also control the direction of air to each rotor stage to obtain the maximum possible compressor blade efficiency. Shown in Figure 1, 48. Are the rotor and stator elements of a typical axial flow compressor. The first stage rotor blades can be preceded by an inlet guide vane assembly that can be fixed or variable. The guide vanes direct the airflow into the first stage rotor blades at the proper angle and impart a swirling motion to the air entering the compressor. This pre-swirl, in the direction of engine rotation, improves the aerodynamic characteristics of the compressor by reducing drag on the first stage rotor blades. The inlet guide vanes are curved steel vanes usually welded to steel inner and outer shrouds. End of page 1 to 40. At the discharge end of the compressor, the stator vanes are constructed to straighten the airflow to eliminate turbulence. These vanes are called straightening vanes or the outlet vane assembly. The casings of axial flow compressors not only support the stator vanes and provide the outer wall of the axial path the air follows, but they also provide the means for extracting compressor air for various purposes. The stator vanes are usually made of steel with corrosion and erosion resistant qualities. Quite frequently, they are shrouded, enclosed, by a band of suitable material to simplify the fastening problem. The vanes are welded into the shrouds, and the outer shroud is secured to the compressor housing inner wall by radial retaining screws. The rotor blades are usually made of stainless steel with the latter stages being made of titanium. The design of blade attachment to the rotor disc rims varies, but they are commonly fitted into discs by either bulb type or fir tree methods. Figure 1:49. The blades are then locked into place by differing methods. Compressor blade tips are reduced in thickness by cutouts, referred to as blade profiles. These profiles prevent serious damage to the blade or housing should the blades contact the compressor housing. This condition can occur if rotor blades become excessively loose or if rotor support is reduced by a malfunctioning bearing. Even though blade profiles greatly reduce such possibilities, occasionally a blade may break under stress of rubbing and cause considerable damage to compressor blades and stator vane assemblies. The blades vary in length from entry to discharge because the annular working space, drum to casing, is reduced progressively toward the rear by the decrease in the casing diameter. Figure 1:50. This feature provides for a fairly constant velocity through the compressor, which helps to keep the flow of air constant. The rotor features either drum-type or disc-type construction. The drum-type rotor consists of rings that are flanged to fit one against the other, wherein the entire assembly can then be held together by through bolts. This type of construction is satisfactory for low-speed compressors where centrifugal stresses are low. The disc-type rotor consists of a series of discs machined from aluminum forgings, shrunk over a steel shaft, with rotor blades dovetailed into the disc rims. Another method of rotor construction is to machine the discs and shaft from a single aluminum forging, and then to bolt steel stub shafts on the front and rear of the assembly to provide bearing support surfaces and splines for joining the turbine shaft. The drum-type and disc-type rotors are illustrated in figures 1:50 and 1:51, respectively. The combination of the compressor stages and turbine stages on a common shaft is an engine referred to as an engine spool. The common shaft is provided by joining the turbine and compressor shafts by a suitable method. The engine spool is supported by bearings, which are seated in suitable bearing housings. As mentioned earlier, there are two configurations of the axial compressor currently in use, the single rotor/spool and the dual rotor/spool, sometimes referred to as solid spool and split spool, two-spool, dual spool. One version of the solid spool, one-spool, compressor uses variable inlet guide vanes. Also, the first few rows of stator vanes are variable. The main difference between variable inlet guide vane, VIGV, and a variable stator vane, VSV, is their position with regard to the rotor blades. VIGV are in front of the rotor blades, and VSV are behind the rotor blades. The angles of the inlet guide vanes and the first several stages of the stator vanes can be variable. During operation, air enters the front of the engine and is directed into the compressor at the proper angle by the variable inlet guide and directed by the VSV. The air is compressed and forced into the combustion section. End of page 1-41. A fuel nozzle that extends into each combustion liner atomizes the fuel for combustion. These variables are controlled in direct relation to the amount of power the engine is required to produce by the power lever position. Most turbofan engines are of the split-spool compressor type. Most large turbofan engines use a large fan with a few stages of compression called the low-pressure spool. These turbofans incorporate two compressors with their respective turbines and interconnecting shafts, which form two physically independent rotor systems. Many dual rotor systems have rotors turning in opposite directions and with no mechanical connection to each other. The second spool, referred to as the high-pressure spool and is the compressor for the gas generator and core of the engine, supplies air to the combustion section of the engine. The advantages and disadvantages of both types of compressors are included in the following list. Even though each type has advantages and disadvantages, each has its use by type and size of engine. The centrifugal-flow compressor's advantages are: 1. High pressure rise per stage. 2. Efficiency over wide rotational speed range. 3. Simplicity of manufacture and low cost. 4. Low weight, and 5. Low starting power requirements. End of page 1-42. The centrifugal-flow compressor's disadvantages are: 1. Its large frontal area for a given airflow and 2. Losses in turns between stages. The axial-flow compressor's advantages are: 1. High peak efficiencies. 2. Small frontal area for given airflow. 3. Straight-through flow, allowing high ram efficiency, and 4. Increased pressure rise by increasing number of stages, with negligible losses. The axial-flow compressor's disadvantages are: 1. Good efficiencies over only narrow rotational speed range. 2. Difficulty of manufacture and high cost. 3. Relatively high weight, and 4. High starting power requirements, partially overcome by split compressors. Diffuser. The diffuser is the divergence section of the engine after the compressor and before the combustion section. It has the all-important function of reducing high-velocity compressor discharge air to increased pressure at a slower velocity. This prepares the air for entry into the flame-burning area of the combustion section at a lower velocity so that the flame of combustion can burn continuously. If the air passed through the flame area at a high velocity, it could extinguish the flame. Combustion section. The combustion section houses the combustion process, which raises the temperature of the air passing through the engine. This process releases energy contained in the air-fuel mixture. The major part of this energy is required at the turbine or turbine stages to drive the compressor. About 2/3 of the energy is used to drive the gas generator compressor. The remaining energy passes through the remaining turbine stages that absorb more of the energy to drive the fan, output shaft, or propeller. Only the pure turbojet allows the air to create all the thrust or propulsion by exiting the rear of the engine in the form of a high-velocity jet. These other engine types have some jet velocity out the rear of the engine, but most of the thrust or power is generated by the additional turbine stages driving a large fan, propeller, or helicopter rotor blades. The primary function of the combustion section is, of course, to burn the air-fuel mixture, thereby adding heat energy to the air. To do this efficiently, the combustion chamber must A. Provide the means for proper mixing of the fuel and air to assure good combustion. B. Burn this mixture efficiently. C. Cool the hot combustion products to a temperature that the turbine inlet guide vanes/blades can withstand under operating conditions, and D. Deliver the hot gases to the turbine section. The location of the combustion section is directly between the compressor and the turbine sections. The combustion chambers are always arranged coaxially with the compressor and turbine regardless of type, since the chambers must be in a through-flow position to function efficiently. All combustion chambers contain the same basic elements. 1. Casing. 2. Perforated inner liner. 3. Fuel injection system. 4. Some means for initial ignition. 5. Fuel drainage system to drain off unburned fuel after engine shutdown. There are currently 4 basic types of combustion chambers, variations within type being in detail only. These types are: 1. Can type. 2. Can-annular type. 3. Annular type. 4. Reverse flow type. The can-type combustion chamber is typical of the type used on turboshaft and APUs. Figure 1:52. Each of the can-type combustion chambers consists of an outer case or housing, within which there is a perforated stainless steel, highly heat-resistant, combustion chamber liner or inner liner. Figure 1:53. The outer case is removed to facilitate liner replacement. Older engines with several combustion cans had each can with interconnector, flame propagation, tube, which was a necessary part of the can-type combustion chambers. Since each can is a separate burner operating independently of the other cans, there must be some way to spread combustion during the initial starting operation. This is accomplished by interconnecting all the chambers. As the flame is started by the spark igniter plugs in 2 of the lower chambers, it passes through the tubes and ignites the combustible mixture in the adjacent chamber and continues until all the chambers are burning. End of page 1-43. The flame tubes vary in construction details from one engine to another, although the basic components are almost identical. Figure 1:54. The spark igniters previously mentioned are normally 2 in number and are located in 2 of the can-type combustion chambers. Another very important requirement in the construction of combustion chambers is providing the means for draining unburned fuel. This drainage prevents gum deposits in the fuel manifold, nozzles, and combustion chambers. These deposits are caused by the residue left when the fuel evaporates. Probably most important is the danger of afterfire if the fuel is allowed to accumulate after shutdown. If the fuel is not drained, a great possibility exists that, at the next starting attempt, the excess fuel in the combustion chamber will ignite and exhaust gas temperature will exceed safe operating limits. The liners of the can-type combustors have perforations of various sizes and shapes, each hole having a specific purpose and effect on flame propagation within the liner. Figure 1:52. The air entering the combustion chamber is divided by the proper holes, louvers, and slots into two main streams, primary and secondary air. The primary or combustion air is directed inside the liner at the front end, where it mixes with the fuel and is burned. Secondary or cooling air passes between the outer casing and the liner and joins the combustion gases through larger holes toward the rear of the liner, cooling the combustion gases from about 3,500 degrees Fahrenheit to near 1,500 degrees Fahrenheit. To aid in atomization of the fuel, holes are provided around the fuel nozzle in the dome or inlet end of the can-type combustor liner. Louvers are also provided along the axial length of the liners to direct a cooling layer of air along the inside wall of the liner. This layer of air also tends to control the flame pattern by keeping it centered in the liner, thereby preventing burning of the liner walls. Figure 1:55 illustrates the annular combustion chamber liner. Some provision is always made in the combustion chamber case for installation of a fuel nozzle. The fuel nozzle delivers the fuel into the liner in a finely atomized spray. The more the spray is atomized, the more rapid and efficient the burning process is. Two types of fuel nozzle currently being used in the various types of combustion chambers are the simplex nozzle and the duplex nozzle. The construction features of these nozzles are covered in greater detail in Chapter 2, Engine Fuel and Fuel Metering Systems. The spark igniter plugs of the annular combustion chamber are the same basic type used in the can-type combustion chambers, although construction details may vary. There are usually two igniters mounted on the boss provided on each of the chamber housings. The igniters must be long enough to protrude from the housing into the combustion chamber. The burners are interconnected by projecting flame tubes which facilitate the engine starting process as mentioned previously in the can-type combustion chamber familiarization. The flame tubes function identically to those previously discussed, differing only in construction details. The can-annular combustion chamber is not used in modern engines. End of page 1-44. The forward face of each chamber presents 6 apertures, which align with the 6 fuel nozzles of the corresponding fuel nozzle cluster. Figure 1:56. These nozzles are the dual orifice, duplex, type requiring the use of a flow divider, pressurizing valve, as mentioned in the can-type combustion chamber discussion. Around each nozzle are pre-swirl vanes for imparting a swirling motion to the fuel spray, which results in better atomization of the fuel, better burning, and efficiency. The swirl vanes function to provide two effects imperative to proper flame propagation. 1. High flame speed, better mixing of air and fuel, ensuring spontaneous burning. 2. Low air velocity axially, swirling eliminates overly rapid flame movement axially. The swirl vanes greatly aid flame propagation, since a high degree of turbulence in the early combustion and cooling stages is desirable. The vigorous mechanical mixing of the fuel vapor with the primary air is necessary, since mixing by diffusion alone is too slow. This same mechanical mixing is also established by other means, such as placing coarse screens in the diffuser outlet, as is the case in most axial-flow engines. The can-annular combustion chambers also must have the required fuel drain valves located in 2 or more of the bottom chambers, assuring proper drainage and elimination of residual fuel burning at the next start. The flow of air through the holes and louvers of the can-annular chambers is almost identical with the flow through other types of burners. Figure 1:56. Special baffling is used to swirl the combustion airflow and to give it turbulence. Figure 1:57 shows the flow of combustion air, metal cooling air, and the diluent or gas cooling air. The airflow direction is indicated by the arrows. End of page 1-45. The basic components of an annular combustion chamber are a housing and a liner, as in the CH.1 type. The liner consists of an undivided circular shroud extending all the way around the outside of the turbine shaft housing. The chamber is constructed of heat-resistant materials, which are sometimes coated with thermal barrier materials, such as ceramic materials. The annular combustion chamber is illustrated in Figure 1.58. Modern turbine engines usually have an annular combustion chamber, as can be seen in Figure 1.59. The annular combustion chamber also uses louvers and holes to prevent the flame from contacting the side of the combustion chamber. A reverse flow combustor is a type of combustor in which the air from the compressor enters the combustor outer case and reverses its direction as it flows into the inner liner. It again reverses its direction before it flows through the turbine. Reverse flow combustors are used where engine length is critical. Turbine section. The turbine transforms a portion of the kinetic, velocity, energy of the exhaust gases into mechanical energy to drive the gas generator, compressor, and accessories. The sole purpose of the gas generator turbine is to absorb approximately 60 to 70% of the total pressure energy from the exhaust gases. The exact amount of energy absorption at the turbine is determined by the load the turbine is driving, i.e., compressor size and type, number of accessories, and the load applied by the other turbine stages. These turbine stages can be used to drive a low-pressure compressor, fan, propeller, and shaft. The turbine section of a gas turbine engine is located aft, or downstream, of the combustion chamber. Specifically, it is directly behind the combustion chamber outlet. The turbine assembly consists of two basic elements: turbine inlet guide vanes and turbine disc. Figures 1.60 and 1-61. The stator element is known by a variety of names, of which turbine inlet nozzle vanes, turbine inlet guide vanes, and nozzle diaphragm are three of the most commonly used. The turbine inlet nozzle vanes are located directly aft of the combustion chambers and immediately forward of the turbine wheel. This is the highest or hottest temperature that comes in contact with metal components in the engine. The turbine inlet temperature must be controlled, or damage will occur to the turbine inlet vanes. After the combustion chamber has introduced the heat energy into the mass airflow and delivered it evenly to the turbine inlet nozzles, the nozzles must prepare the mass airflow to drive the turbine rotor. End of page 1-46.